Hey guys, Ms. Gosling here. In this video, you're going to learn about diffraction. By the end of the video, you'll be able to describe and solve problems involving single and double slit diffraction. So let's go ahead and get started, shall we? So let's start by talking about what diffraction is. So diffraction is going to be defined as the bending of bending of waves around a barrier. Now, specifically what we usually see is waves coming in flat and then seeing a barrier. As they go through the barrier, they condense and then leave the barrier in this lovely semicircular pattern. You can see a really lovely example of it in real life in this picture on the left. So we have those waves coming in from the ocean straight, getting pushed through the barrier and ending up in that semicircular pattern. And that is what our single slit diffraction is going to look like. So in this picture here, you can see what a single slit diffraction pattern looks like. And if we were to zoom into that picture, what we would see is a single bright spot in the middle, surrounded by a dark spot on either side, each dark spot patterned next to a light spot, and so on and so forth throughout that entire diffraction pattern. So we generally define, so when we look at single slit diffraction, we're going to look at our intensity as it relates to the angle between that central point, 0, and the center of each minima, so each of our dark spots. So this, for example, will be theta 1, with the second angle here being theta 2. And again, we can do the same thing on the right side of our bright spot with theta 1 and theta 2. So if we're to create a graph of theta, of angle, versus intensity, what it would look like is the following. We would have our dark spots at theta 2, theta 1 on both sides. And we would see our bright spots kind of increasing and decreasing in brightness over that space. So we're darkest near our angle, near those angles that we define, and we are brightest when we are directly between two angles. So if we take a look at our single slit, we can actually figure out the relationship between the length of our slit, which I'm going to go ahead and call A. So here's my slit of length A, and let's do that in a slightly different color so it's a little easier to see. So what we can actually do is we can figure out the relationship between our angle theta and our the length of our slit, that distance in our slit. And the equation that we're going to use for that is theta is equal to lambda, the wavelength of our light, divided by A, that slit width. Now that is going to be the equation for our first minima. So for theta 1, that's how we will get that angle. If we wanted theta 2, we would have to add an n in here. It would become 2 lambda over A. And so that is going to be I'm going to call that the minima number. So our first angle is going to be lambda over A. The theta 2 is going to be n times lambda over A, or 2 times lambda over A. And we can actually figure this out with the geometry here. We are not going to talk through that though, because it's a bit of a long proof. If you're interested, I'm happy to talk about this with you later in class, however. Now, one last thing I want you guys to know about the single slit is that we can see here that the position of those minima are dependent on, so theta is directly proportional to our wavelength lambda. So as a result, if we send white light through our single slit, what we'll notice is actually white light is going to be broken into colors via diffraction, because each color has a different wavelength. So for example, so what you'll see is something kind of like this. So blue light is going to bend a little less than our red light. So you'll see that purple, green, you'll see a color, a bit of orange as well, which I'm going to go ahead and skip. Actually, no, I won't. Here's some orange. You'll have that yellow between your orange and your red, and then you'll have that red at the end. And of course, we also, of course, have our purple. So you'll see that really nice rainbow at each place except for that central maxima. So every other place of bright light, so this point here, you're going to see that rainbow rather than white light, which is pretty cool. So now that we've talked about the single slit, let's go ahead and take a moment to talk about the double slit. So in our double slit, rather than having a single slit, we're going to have two. So we're shining a light of some kind, in this case red light, directly at between the slits, and that light is going to be broken up between the two slits in that diffractor. So the light's going to go through here, it's going to go through here. And the light that goes through this is going to be projected onto some screen a distance away. I'm going to go ahead and call that distance D, and I'm going to call the distance, we're going to again do that labeling in that nice blue color to make it a little easier to see. And we're going to call the distance between the centers of our slits little d. So what we want to do is figure out the distance between our first central bright spot, because we are again going to have that same central bright spot, which you can see here in our image. We want to figure out the distance between the central bright spot and the next bright spot over, which we're going to call B. Now that distance between them, we're going to call S. So looking at the geometry of the situation, which again, I'm not going to worry too much about, what I'll find is that S must be equal to lambda times big D over little d. So the wavelength, the distance between the central maximum and the first bright spot is going to equal lambda times the wavelength of the light times the distance between the screen and the slits divided by the distance between the slits. So at every point, so we can expand this out. So this is for our first bright spot. If we want to look at other bright spots, what we would say is we're going to add that n in again. So we're going to say S is equal to n lambda d over d, where again n is the number of the bright spot. So how far we are from that central maximum. So if this right here is our central maximum, that'll be n equals 1, and the next one will be n equals 2. And we'll see the same thing on the other side. Now, the other thing that you should be aware of, so again, n must be an integer, and whenever we have n plus 1/2 times lambda d over d, what we'll actually get is our dark spot. So we'll get the center of our dark spots by doing this. Now, you're not going to really be asked to do that much. In fact, most of the time, you'll only be using that first equation. But I do want you to make sure that you know that we have that our center spot, that we can look at spots other than our first one, and that directly between our bright spots, we have a dark spot. Now, the reason we are getting this is because our light, when it goes through those two separate paths, is going to have either constructive or destructive interference, right? So we're going to have our light going out like this and like this. So when we have constructive interference, we'll get those bright spots, and you can see they're much more defined than in our single slit. When we have destructive interference, we'll have those dark spots. And again, you can see they're so much more clearly defined than in our single slit. So this double slit is actually going to be far more useful for measuring the wavelength of light than our single slit is, just because that diffraction pattern is much easier to read. So I do want to take one moment to just mention that the double slit experiment is also one of the coolest experiments for seeing the wave-particle duality of light. So the fact that light acts both as a particle and as a wave. So that diffraction pattern we get when we send our light through that double slit occurs because of interference, because we have places of complete destructive interference and complete constructive interference. So we have those bright spots and those dark spots. However, so the question would be then, what happens if I send a single photon through? So I'm going to go ahead and call this, so I'm going to go ahead and send one photon through my slit, my double slit. And what I'll actually notice is if I don't measure which slit the photon goes through, I will still get that same diffraction pattern. And that is because our photon somehow manages to kind of go through both slits and one at the same time. So until we measure which slit that photon goes through, what we'll see is that exact same diffraction pattern we got with a full wavelength of light, even though there is no interference going on because the photon cannot interfere with itself. However, as soon as we add a meter to see between our that measures that can measure which slit the photon went through, at that point we no longer have single slit diffraction, or we no longer see our double slit diffraction pattern, and instead we see the pattern for a single slit. So what this tells us is that this actually tells us a lot about quantum mechanics. So the reason that photon can interfere with itself is because it exists primarily as a probability wave, not as an actual physical thing. So until we measure which slit it went through, it went through both. And it's that very act of measuring which slit it went through that changes what it did. And this is such a crazy thing because this suggests that the act of taking measurements in physics, taking measurements of the physical world, changes the physical world. It has that fundamental change in that physical world. So this is one of the big, interesting mysteries of physics. You should not get asked about this on your IB exam, but it is one of the most interesting things I think out there. So I wanted to make sure to take a moment to share it with you as well, because I think it is beautiful, it is mysterious, and it's something that makes me wonder a lot about what measurement really means. So, takeaways. Diffraction occurs when waves bend around a barrier, and we have very clear and distinct diffraction patterns for a single slit and for a double slit diffraction. The double slit experiment is also a great example of the wave-particle duality of light, so the fact that light can act both as a particle and as a wave. So with that, you now know about the single slit and the double slit experiment. It is now your turn to try solving some problems. Best of luck, and happy solving!